Hey there, it's me. I have a little video here of me. This is the beginning. I don't know what I was just want to add something different, try out something new. But I went over the electric field due to a dipole along the axis of the dipole, and now I'm going to do the same thing except for perpendicular to the axis of the dipole. I told you I'd do that, so now I'm going to do that. Okay, so let me go over here to my paper. I'm going to turn this off. I don't think you really need to see that. Let's see. How do I? Yeah, no, it's just right here. Good. Okay. So here's what I have. I have a dipole. A dipole consists of two charges, a positive and a negative Q, and I put the positive on the x-axis just like that. And I want to find the electric field at this point up here, RO. And so I have the electric field due to a point charge is 1 over 4 pi epsilon naught Q over the magnitude of R times the unit vector R hat. So this is, if here's my point charge and there's my observation location, then this is the vector R from the point to that observation location, and then you can find the electric field. Now, I actually want to write this out a little bit differently. So if R hat is defined as the magnitude of R divided by the vector R divided by the magnitude of R. That's true. That's how we define the unit vector R hat. So if I put that in up here, I get this. E equals 1 over 4 pi epsilon naught, which is just a constant, Q over, now I'm going to have R hat is going to be R, and this is going to be R magnitude times R magnitude squared, so R cubed. It's the same equation, okay? But this is going to be a little bit easier to deal with. So what we're going to do is we're going to come over here, and I'm going to calculate first this vector R, I'll call that R plus. That's the vector from the positive charge to the observation location, and I can find the electric field due to that, and I should put it in red, right? I remember so this is going to be E plus. And then I can do the same thing for the negative charge. I need to find R minus. And then from that, I can find E minus, which is actually going to be this way. And then the total electric field, E, is going to be E plus E minus. I was going to do those in different colors, but I just forgot. Okay. So let's calculate E plus. So the first thing I need to do is let's pick my observation location. Let's say RO, it's on the y-axis. So I'm going to write this as 0, y, 0. And that's the distance y up here. So it's on the y-axis, some value y. Now I'm going to find, if this is the S is the distance between these two charges, then the RQ plus is the location of the positive charge, and that's going to be equal to S over 2, 0, 0. So R plus is going to be equal to the final position, which is this, minus the initial position of that. So this is going to be equal to 0, y, 0, minus S over 2, 0, 0. And I guess I should point out that I'm using this angle bracket notation for vectors. It's what's used in matter interactions, and it's just something that way. So this is the x, y, and z components. So I can do this, and I get 0 minus s over 2 is going to be negative s over 2. Y minus 0 is y, and 0 minus 0 is 0. So that's my value of R plus. I'm going to also need the magnitude. So R plus magnitude is going to be equal to this squared plus this squared plus this squared square rooted. So it's going to be a square root of s squared over 4 plus y squared plus 0. And you can't see that. Okay, there you go. Let me rewrite that. I didn't realize my paper. Okay, so let's put this over here. R plus magnitude square root of s squared over 4 plus y squared. So now I could put that in to my equation here. So I'm going to say E plus, it's going to be 1 over 4 pi epsilon naught Q. R is going to be this. So that's going to be equal to negative s over 2 y 0. And then I'm going to have r magnitude cubed. So it's going to be this. It's going to be this value cubed. So it's actually going to be s squared over 4 plus y squared square rooted cubed, so to the 3/2 power. And that's important. So I'm going to put a box around that. Okay, now let's do the exact same thing for the electric field due to the negative charge on a new sheet of paper right here. And I have to make sure I'm all aligned. So the first thing I want to do is, let's draw this picture again. So there's my point charge. Here's minus q. And I want to find this vector, r minus. So r minus is going to be equal to r, let's write these other things out first too. RQ minus is the vector location of this. It's going to be equal to negative s over 2, 0, 0. And the observation location, RO, is going to be equal to 0, y 0. So this is going to be the final position, R0, minus initial of that. So I get 0, y 0, minus negative s over 2, 0, 0. This is going to be equal to 0 minus negative s over 2 is s over 2, y 0. And then the magnitude of that's going to be the same thing. R minus magnitude is going to be the square root of s squared over 4 plus y squared. Now I can put this into my new equation, E minus 1 over 4 pi epsilon naught times negative q, because it's a negative value, divided by this stuff squared. So that's going to be s squared over 4 plus y squared to the 3/2. And then I have the vector right here, s over 2, y 0. And it's important, so I'm going to put it in a box. Okay, now let's go back and bring my other equation, E plus, I'm going to rewrite that. 1 over 4 pi epsilon naught positive q over s squared over 4 plus y squared to the 3/2. And this was negative s over 2, y 0. Now I want to add these two together. And so they're both vectors. So let's add them as vectors. Let's start from the z component. So the z component for E minus is 0. The z component for E plus is 0. So who cares, right? Those are 0. What about this? Here I have y and there I have y. And over here I have 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught, negative q, s squared over 4 plus y squared to the 3/2. So everything is the same except in the y direction, this one's negative and this one's positive, so they're actually going to cancel. And if you look back over here to my initial picture, that makes sense, right? Because these have the same magnitude because they're the same distance, and so the y component should cancel. And we should just get a vector going in the negative x direction. And that looks like what happens there. It is what happens there. So the x and the y components are 0. So I only have to deal with the y and the z components are 0. So let's just write down ex, the x component. It's going to be 1 over 4 pi epsilon naught. And then the x component for this one is going to be equal to q over s squared over 4 plus y squared to the 3/2. And then I have this negative s over 2. That's the from the top part, that's the x component. Then I have to add in this one, which is going to be plus 1 over 4 pi epsilon naught negative q over s squared over 4 plus y squared to the 3/2 s over 2. And you'll notice here that I have this is the same as this, because I have the negative sign right there. Here I have the negative sign right there. So I just add these two together, and I have s over 2 plus s over 2 is going to give me s. So I get negative 1 over 4 pi epsilon naught qs over s squared over 4 plus y squared to the 3/2. Now, and I did it again. Okay. I need to work. Maybe I can zoom out my camera a little bit. Now I can take the case where y is much greater than s. If that's the case, I have this term down here, s squared over 4 is going to be very small compared to y squared. So I get ex is approximately negative 1 over 4 pi epsilon naught qs over, now I'm going to get, this is just going to be 0, and I get y cubed, y squared to the 3/2 is going to be y cubed. And that's my answer. So I could write this in a different form. I could say E perpendicular, because it's perpendicular to the axis of the dipole. Magnitude is going to be 1 over 4 pi epsilon naught qs over r cubed. And notice it does have the correct units, the same units as the electric field due to a point charge. It's charge over distance squared, except distance over distance cubed. Okay, so now let's go and plot this. Okay, I'm going to switch over to Python and make a plot. And I did this before, but I want to do it again. I'm going to do it a little bit differently. So here's what I'm going to do. I'm going to give a vector value for, I'm going to use a charge. I think I'd had a 1 millimeter separation, so I had it like this. So this is negative 1 nanocoulomb at lowercase plus 1, and this was S is 0.001 meters. And so what I'm going to do is have my observation location, I'll call it RO. I'll have this as a vector, I'll have this as a vector. I'm going to do everything as vectors, which I didn't do before. And then I'm going to plot the vector, the electric field in the x direction as I move further and further away compared to my answer. Okay, so let's switch over to Python. Let's see if I can do this. Oh, I didn't set this up correctly. Oh, shoot. Okay, no, it is. Okay. Actually, I think, let's see. If I go to new trinket, I think it might be too big, but no, I didn't want to do that. New trinket, glow script. Oops, it didn't. It's a little slow. Okay, new trinket, glow script. I think it might be working. Python. Oh, I hit myself. Python. Okay, I think this is good enough. Let's see if I move this over. See if I move it over here. And there we go. Okay, that's going to be good. Okay, let me move my board. Okay, now I'm switched over, and I apologize for the transition, but this way I don't have to edit. Okay, so I'm going to go ahead and say Q equals 1 times 10 to the negative 9th. 1 times 10 to the negative 1 nanocoulomb. And then I'm going to say K is 9 times 10 to the 9th. So equals, and I should make this a little bit bigger. No, that's smaller. Okay, that's good. And S is equal to 0.001. So now the first thing I'm going to do is I'm going to make a vector position. I'm going to say RQP for plus. That's the vector location of the positive charge. And that's going to be equal to vector. The positive was S over 2, 0, 0. I'm going to also need to make a graph. So let's just go and put that up in here. T graph equals graph. I'm having typing problems. Graph. Graph. X title is going to be equal to Y. Let's just call it Y. And then Y title is going to be E. Let's just leave it like that. And then I'm going to make two graphs. I'm going to make FE is a G curve. And the other one is FA is a G curve. And so the blue is going to be the exact calculation, and the A is going to be the approximation. Okay, so now down here, I also need the location of the negative charge. RQN is the negative charge vector, spell it correct, negative S over 2, 0, 0. And then the observation location RO is going to be equal to vector 0, Y, 0. And I didn't pick Y, so I need to go ahead and pick that up here. So let's say Y equals, let's see if they're 0.01 apart. Let's put 0.002, and I need dy is 0.0001. Okay, equals. I'm having an equal problem here. And that's just where it's going to start. Okay, so now the first thing I'm going to do is calculate E plus. It's going to be equal to K times Q times, let's write this out the same. Oh, I need to find RQ, RP. RP is the vector from the positive to the observation location. So it's going to be RO minus RQP. And then RN, the negative, is going to be RO minus RQN. So this is going to be RP divided by the mag of RP cubed. Right, that's what we said. That's the equation for the point charge, the electric field due to a point charge. It's a vector, okay, because RP is a vector. Now I can do the same thing for R minus. E minus is going to be equal to negative K times Q, because the Q is negative now, times Rn divided by the mag Rn cubed. And then E is just going to be equal to EP plus EM. Okay, now that's all great and everything, but what I want to do is change this and plot it. And let's also calculate E approximation is going to be equal to I'm going to write it as a vector too. So this is going to be equal to K times Q times S divided by Y cubed. And then I need to multiply this as a vector, vector negative 1, 0, 0, because it was in the negative x direction, and I knew that. Okay, so now I want to make a graph. So let's go over here and say while y is less than 0.007. And then I'm going to calculate RO. I need to recalculate this because I'm going to be changing y. And then I need to recalculate EP, recalculate E minus, recalculate the total and the approximation, and then plot them. So FE dot plot x, and the y coordinate is going to be E dot x. I can't plot the vector E. I can plot an x component of the vector E. And then FA dot plot is going to be x EA. What did I call it? EA dot x. And then I need to increase the y value. Y equals y plus dy. Okay, let's save this and see if it works. I didn't give it a name. That was my mistake. I'll change the name. I'm going to give you this code too. Okay, now I'm going to run it. This is the scary part. Yep, I got an error. X is not defined at or near line 26. Oh, Y. This is supposed to be Y. Dummy. Yeah, check that out. Okay, so let's see, does this make sense? As Y gets greater, the electric field gets smaller, and these two diverge. Okay, so this is exactly what we would expect. It is a negative x component, and as it gets further and further away, these two values get closer and closer together. So around here at about this value of 3 millimeters, there's not that much difference in the two answers. But as you get closer and closer to the actual value, it does go away. And in fact, you could go all the way down to 0, right? Because if I went to y equals 0, I can actually calculate the exact electric field, but I can't calculate the other one. That's actually a really good problem. What is the electric field in the center? It's not 0. I can't do it for the other approximation because I'd have dividing by a 0 value, and I don't want to do that. So, okay, so there you go. That's the electric field due to a dipole on an axis perpendicular to the dipole. I do have some other things to do. We're going to do a visualization of the electric field in 3 dimensions using GlowScript, and I'll make that as another video. So you'll just have to wait for that. It's going to be awesome, and I'll talk to you guys later.